I'm here in Shenzhen, China to go meet the ex-VP of R&D from DJI to see what he's building for his new product at his new company. A big shout out to Morpho for sponsoring this video. Let's go. Brett, good to see you again.
Good to see you again. Welcome to Morpho.
Thank you. I'm really looking forward to seeing what you guys have.
This is our Morpho UV printer. It can do something that others can't, because most UV printers can print textures. But this one, because we have 4 cameras inside it, we use 3 out of the 4 cameras to scan the texture of your own object, and then we can replicate that.
Oh, amazing. Okay.
Here's the cookie. You want to scan it, and then we replicate it.
This feels very sci-fi right now. All right.
Yes.
So it's been about 47 minutes. Let's give it a look. Oh, okay. Sweet. Oh, that's pretty cool. You can see all of the texture in the M&Ms and the cracks in the cookie. That's pretty cool. So you guys have, one of your samples is oil paintings. So the idea is that you could replicate an oil painting, including the texture of the brushstrokes, which I think is so cool. It feels very like sci-fi. So you have a very interesting story for this. I want to hear where you came up with the idea for this printer and where you got started.
So it started more than 2 years ago. I was trying to help my daughter with her presentation in kindergarten. The topic was how to make something. And then we chose the topic, how to make stickers. Originally, I print on, I use a traditional printer. I print on paper that has a glues on the backside of it.
Yeah.
And then she was not satisfied with that. I brought the industrial level one.
Industrial level UV printer.
Yes, I kind of did like this. And then my wife didn't allow me to put it at home because it's so big. And then it's very smelly. When it's working, you see the UV light shining your entire room. We can't let our children staring at the UV light. So at day one, our principle is to try to enclose the printing area while the machine is working. Yes, and then to prevent people from the UV light, from the smell, I come up with this technology.
What's your background? What did you do before this?
I was the VP of R&D at DJI, making drones. I was the product manager of Phantom 2 Vision and Phantom 2 Vision Plus.
So you have a real background in consumer electronics and really taking consumer electronics to market. I want to understand what your process is when you went from, okay, I bought this and it doesn't meet my needs, to, okay, I want to turn it into a product.
I felt the UV printer 2 years ago was very similar to the drone industry 15 years ago. People have the demands. As a consumer, I have the needs as well. But the problem is the machine, the product there, it's still industrial level. It's very big, very expensive. The software is very crappy. So I think we can do something much better. Traditional UV printer, you have the print head moving in the X direction, the flat bed is moving in the Y direction. If you want to enclose the whole machine, you actually need twice the area.
Oh, sure, because you have to be able to move all the way to one side and then all the way to the other.
That's impossible to make a larger size. We adapt this so-called gantry structure so that the print head moves in both X and Y direction. Your print bed doesn't need to move, so that we can maximize the printable areas.
Yeah, okay. So you have some of your early prototypes here.
Yes. This one was what we call a proof of concept. We try to figure out what software we need, what algorithms we need. At the moment, we didn't figure out what the printable size should be.
Tell me a little bit about how this is built. This is aluminum?
Yes, it's CNC.
And so you have just a bunch of CNC'd plates, essentially, that bolt together for this?
The rigidness is not very good, and then the precision of the movement of the print head is not very good. We just assembly everything together. Because we have stereo vision cameras, actually your entire area needs to be protected so that it won't be affected by the environmental light. Even the position of the ink cartridges is very important. If it's too high, then it will lead to the leakage of inks from your print head. If it's too low, then there are no enough inks.
So you knew even at this first printer that you were going to include stereoscopic cameras?
From day one, for UV printers, the machine doesn't know where you put the object. When I try to print on jigsaw puzzles, it's very difficult to do the alignment. So I need to use a ruler to do a lot of measurements. Sometimes I make mistakes. Then I waste the blank jigsaw puzzles. So we need a way that first to measure the height of the object so that your print head won't crash into the
Right, because
object.
you might have something that's this small, you might have something. How high can you guys print?
16.8 centimeters. So zero vision cameras are like our human eyes. We see things differently, our two eyes, right? So based on these disparities, we can tell how far away from the object, right? So in that way, we can measure the height of the object. So that happens like within 1 second. That's the fast scanning. But for the professional scanning, the slow one, then we use different pictures to stitch them together.
Oh, and you're using the same camera but moving it over a little bit to
Yes,
get a
yes.
stereoscopy image
Yes, exactly.
with the same camera.
In that case, you have higher resolution.
Sure.
The zero vision cameras can also measure the contour of the object, the outline. So it knows where to print on and where they cannot print on.
Okay.
Then on your software side, you just need to drag and drop your design towards the object. So A4 or slightly larger than US letter size is sufficient for in most cases. But we do have an A3 extendable bed in our final product.
For the Americans is bigger than A4. Yeah. Awesome. So this was the second one.
We shrink the size of the printable bed. For the Z-axis, we use lead screw. And then we have double Y-axis. We use linear guide rails for the Y-axis. We tried different options. Originally, we tried two different motors to use software to control them moves together at the same time. But later on, we changed to one motor. So then we came to the third one. For this one, we already integrated the zero vision cameras. And then you see all the lightings here. We've done lots of tests on where should we put the lightings to minimize the reflection, minimize the shadows.
And is this now custom circuit boards?
Yes.
That you're developing yourself?
Yes,
Okay.
Yes. We have like FPGAs and then microprocessors as well.
Got it. And what are you using FPGAs for?
For communicating with the print head. And then here we already fixed the location of the ink cartridges. And then other stuff, we have the laser for collision avoidance.
Why do you also need the laser?
Sometimes when you print on acrylic or some wood, because of the shrinkage of the UV inks, they will have a very large shrinkage force. And also sometimes your UV light will heat up the material. All this will cause the material to bend or warp.
So this is like a safety barrier, a safety light barrier, so that if it starts to warp up where it'll hit the print head.
And then we have their internal air filtration system already built in.
To remove the VOCs, the volatile fumes from the ink.
So this one was already very similar to what we have right now.
Yep.
So we have the wiper clothes integrated. After you do some printing, the surface of the print head might be very messy, full of UV inks. So you want to actually wipe those things out. Traditional UV printers, they use a rubber so that like when your print head is moving in the X direction, so every time it's cleaning the print head surface.
Like a windshield wiper on a car.
Yes, but the problem is the distribution of your print head nozzles is actually in vertical lines. So in that way, you're actually pushing one color to another. And then fortunately, we have this gantry structure. We can move in the Y direction. Yes, so that we have this wiper clothes. If there's a roll inside, yes, so that we can clean it in a much better way.
By adding that Y direction, now you can actually choose to wipe in the other direction that existing printers cannot. So why did you not just put a piece of rubber there and wipe in the Y direction?
We've done lots of reliability tests. So using this way, it's much better for the print head itself. You don't want to exert too much pressure on that. And then how about the waste? All the waste is actually on the surface.
You're just building up this gunk on the...
Yes, and then sometimes the waste ink will be cured.
What's your current solution?
It's like a special type of clothes, so that the UV ink will just go inside the micro holes inside the clothes.
So what's this?
Pretty much the final version of the UV printer, yes.
Can we open this?
Yes.
Does it move? Okay. Was this 3D printed? Is this like SLA?
It's CNC.
It's CNC?
In pieces, and then they combine and glue the
Oh, I see.
parts
Oh, so
together.
these are the glue seams. So you're seeing this out of blocks of plastic. That must cost you a fortune.
Especially that one.
How long did it take you from starting your first prototype to here? How much time is this?
More than 1 year and a half. At that moment, we were 5 or 6 engineers at the very beginning, and now we have more than 130 engineers.
This is just crazy to me. You're not going to CNC the final versions, right? So why do CNC?
To do some faster prototyping, because 3D printing, sometimes you won't get the accuracy, especially for big components, like large components like this. So yes.
Because of shrinkage?
Shrinkage, and also about the material itself. Some of the internal parts are also CNC.
So just to give people some idea, to have the enclosure for this made out of CNC, how much roughly are you talking for one?
Like from 5,000 to 10,000 US dollars, just for the shell.
Whoa!
Yes, it's super expensive.
Wow, that's wild. So this one is sort of to get the structure right. And then this finally is the one that looks like what you're gonna ship, right?
Yes.
But this one is still CNC'd?
CNC.
CNC'd, okay. And then once you verify this, then you will start making your tooling?
Yes.
Is that right?
Exactly.
Yeah.
Actually, we are already in the process of molding.
Got it, okay.
Yeah.
Let's go back over here. I want to ask you about print heads, because I know they're super important to this whole thing. My understanding is that it's a little bit like the print head in your home inkjet printer.
They are slightly different. Your inkjet printer at home, they are designed for water-based print head. For UV printers, the UV inks are actually highly corrosive. If you just leave your UV ink inside the print head for just 1 or 3 months, your print head will go dead.
So my understanding is that the home inkjet printers, they have a block of silicon, right?
yes.
And they have tiny tubes in them that the ink comes out of, and then they have like a resistive coil essentially around it that heats up the ink, and that just makes it bubble, like makes it boil, and it pops out of the hole.
Yes.
Is that how these work?
Unfortunately, those kind of print heads cannot be used for UV inks because the temperature goes more than 160 Celsius degrees.
And then it changes the ink? Is that the problem? Okay. Yeah. How do these work?
It's called piezo. You have a special type of material. So if you have a voltage on that material will kind of shrink or reshape. If you need inject a droplet at this location, then it triggers a signal and it triggers the piezo to deform itself.
That forces the ink out? Okay. And so are you making your own print head, or how does that work?
No, we are using like from Epson. We need to make this affordable to users, right?
Sure.
So that's why they chose Epson print head called F1080. And the F1080 was very popular among Epson home use printers.
Okay.
The existing UV printers, desktop UV printers, they have like cleaning cartridges as well as moisture lacquer cartridges. At night, if you don't do any printing, so it will pump out all the UV inks inside the tubes and inside the print heads.
Yeah. And that's your cleaning fluid?
Yes, you use your cleaning liquids to flush the entire system. But unfortunately, cleaning liquid is also highly corrosive. Then you need to pump out all the cleaning liquid and then fill up with the moisture liquid.
And that's kind of a neutral solution that doesn't erode it.
Exactly.
Got it. Okay.
But if you want to do the printing, then you need to reverse the whole process.
Got it.
So that causes a lot of waste.
What did you do that was different from these other printers?
We developed our own ink that is not corrosive to the water-based print head.
And so does that mean you still have to do the cleaning and the moisturizing?
No, we don't have to. We have no cleaning liquid. We have no moisture liquid.
So you can just leave the ink in the nozzle and you're done.
Yes.
Smart.
Yes,
Very smart.
But we do have another option for the user to choose from. We use an Epson high-end industrial level print head. We can achieve higher printing speed. Epson names their print head by the number of nozzles.
Okay.
So F1080 means you have 1,018 nozzles printing at the same time. For the industrial one, it's called I3200. So it has 3,200 nozzles printing at the same time. So you have
3 times as many.
3 times as many. If we talk about the white ink, so we have that 3,200 nozzles have 8 channels. So we have 2 channels of white ink, which means we have 800 nozzles for white ink.
And that's important because white ink is what you use to build up the texture. And so if you're doing a textured print, it's putting down the white ink that takes the most time.
So it's 800 versus 180.
Oh, got it. So now you can build up your white layer way faster.
Yes. And sometimes we use both white ink and also varnish ink to build up the texture layer.
Oh, together you mix them.
Yes, so that is like a 1/600 versus 360. And then the firing speed is also different. The professional one is 1.5 to 2 times of the firing speed.
You were also mentioning there's some issues with white ink.
The component inside the white ink is actually very similar to the one we used for sunscreen. We have different small particles of this titanium oxide. But the problem is small particles aggregate together, so it becomes bigger. And sometimes if it gets bigger than the size of the nozzle, then you block. It's called aggregation.
Oh, so it gets blocked inside the tubes on the printer as well.
Or your diameter becomes thinner and thinner,
Sure.
so that the ink flows slower and slower.
So how are you guys solving that issue?
On the white ink cartridge side, we have a stirring, and then inside the tubes, we have a circulation system.
So you're constantly pumping it around.
Yes. Every day, we do it, pump it for several minutes, it's enough. But the white ink goes all the way from the white ink cartridges to the tubes. Before you go into the print head, there's a damper in between. Fortunately, we have gantry structure. We can shake in the y direction so that we kind of shake inside the damper. Because the damper it's putting like in this direction.
Yeah,
So
okay.
moving in X direction doesn't help.
really shake it up much because it's pretty narrow. So if you can shake it in the Y direction,
Yes.
then you can stir it up
Yes.
inside the chamber.
Yes.
Super smart.
Yes.
So periodically, this thing will just vibrate.
Yes. Quietly.
So one of your solutions, it was to develop your own ink.
Yes.
Let's go take a look at that.
Yes. Let's go.
So how did you guys solve the corrosion issue?
If we look at the components of UV inks, like there are around like 5 different functional, we call it functional components.
Yeah.
Here I have a little short note. The first one is the prepolymers. It acts as the backbone of the UV inks. It determines the resistance, scratch resistance, the adhesion, and also the hardness of the UV ink. And also we have the so-called monomers. That one is the solvent. It decides the viscosity of the UV inks. And then we do have another thing called photo initiators.
Yeah.
So like by the name that it absorbs a certain wavelength of UV light and then cure the UV ink. Yes,
okay.
and then it becomes solid. And then you have different wavelengths of UV light. And then we have the pigments, like if it's
right.
magenta or blue or,
Sure.
or whatever color. And then we have the final last one is the
Additives.
Additives, yes, right.
And what are the additives for?
It has lots of formats, like for example, the leveling agents or like deformers, and then also like we call it adhesion promoters, so that it adds more adhesion.
Yeah, so it sticks better to whatever you're
Yes,
coating.
and all like stabilizer, like it's better for the transportation. For each functional component, you have 20 to hundreds to thousands of different chemical options that you can choose from. So we did a DOE test on every possible chemical option. We permute every possible things and do a test. We've done thousands of tests. Then we were able to get a short list of a subset of chemical options that is not corrosive to the printhead. This is a chemical compound that we can choose from. Then we combine them together, come up with our own solution.
And then presumably at the same time, you have to be testing whether it's actually a good ink in all of the other
of course,
characteristics
like in terms
as well.
of performance,
Sure.
like adherence, scratch resistance, and we do all these tests.
How did you know whether it was corrosive or not?
We measure the volume of the material. Corrosive, then material becomes bigger. That kind of thing. Or some material just vanish, gone.
So you were able to develop one that's not corrosive.
Yes.
And then also I think you were mentioning it's low VOC,
VOC,
as well.
like it's around like 8 to 13% of the VOC emission comparing to the existing market one.
For people that don't know, VOC is volatile organic compound. It's what you would smell coming off of like a paint or a solvent or an ink or something like that, and potentially is pretty harmful to you, right?
Yes.
It can be pretty bad for your health.
Sometimes VOC, you can't smell it. Another issue of the ink is like the pigments do settle to the bottom. Then it creates unevenness of the color performance of your inks.
Got it. And so that causes a color shift then?
Yes, or degrade.
Okay,
Sure. That's from the ink part. And also, as you use the printhead, in the places near each nozzles, maybe small portion of the UV ink already cured. Then you have the diameter of the nozzle shrinked. So every droplet is in different sizes compared with at the very beginning.
Sure.
Every time you inject a droplet, for this nozzle, you have a relatively smaller ink volume. That's why we added spectrum photometer at the bottom of the printhead carriage.
So you can measure your color in the moment.
Yes, you print on some test pages,
Yeah.
and then it's color box, and then you do a measurement of the colors.
Smart.
You can do your own ICC profile, and also you can calibrate your color performance according to what you have. We already got the G7. G7 is called color space. It's the highest standard of how accurate your color is.
Let's head out to your other testing area. I want to talk about how you're starting to turn this into a production line. How you're going to actually make this product and make a bunch of them. So why is it yellow in here?
It's kind of like a filter. We filter out all the UV portion from the lighting, so that like it won't cure our UV inks inside the room.
So you don't clog the nozzles.
Exactly.
So Brett, what is the process of going from the early prototypes to a full production, mass production product?
We have several different stages from our raise of concept to all the way to mass production. You need to raise a concept and to see whether it's a valid business or not. Then we come to the proof of concept stage. At that stage, we need to see if there are any potential risk on the technology side. After that's all the potential risks are cleared out, then we enter engineering validation test. This kind of phase, that's where we have all the different prototypes of the designs.
What's the goal of the engineering of the EVT?
In terms of software, we need to finish all the functionalities of the machine. And in terms of mechanical design, before you finish the EVT, we need to lock all our entire designs. Then we enter the DVT process. DVT is it's design validation test. Most of the components or all the components are already molded. Whether your ECC performance of your hardware can pass all the regulation tests.
So in the EVT, you had the 3D printed parts, the CNC'd parts, not necessarily using the processes that you would use. In DVT, it's really about getting those final processes and the final materials. Is that when you're creating your injection molding tools?
Yes, and then you need to use those injection molded components to finish all these reliability tests, long-lasting tests, all this.
Got it. And so that's when you're really spending a lot of money, right?
Yes.
Okay, so let's talk a little bit about that, right? You said there are a couple milestones within your tooling. Let's talk about those.
T0 is the first time you got the molded parts. Then after you did perform some of the reliability tests, you find some problems, or when you try to assembly them, there are some errors, or the dimension you need to change a little bit. Then you do a little bit modification of your molds.
Oh, to the actual steel mold need to change.
Then we call that T1, T2. And then
I see. So those are the versioning of your tooling.
Yes.
I see. Got it.
Exactly.
I don't want to get too much into your cost structure, but just so people have an idea of the order of magnitude of what we're talking about. There are a bunch of machines in this room. These are all EVT?
EVT.
What does it cost to make one of these?
It's still relatively high because you have all these CNC parts, 5,000 or something, including the print head. But this is EVT units.
And then when you start opening your injection molded tooling, your molds, how much does that cost?
In terms of R&B, it's 10 million RMB to 20 million RMB, something around that.
So that's multiple million US dollars.
Yes.
Wow.
It's because of some of the components are very large in size. So you need a bigger machine.
So really big, they have these big blocks of tool steel that they machine out, which takes a long time. It's very hard steel.
Higher pressure, higher temperature. For example, this part is CNC.
Okay.
Yes, this is CNC. The diagnostic molded.
Okay.
Yes, we can imagine.
So this would be your prototype version for EVT.
Yes.
And then this is your actual die cast. So this is die casted aluminum.
Yes, it's called T0.
And so obviously if you think about the mold that this came out of, it's going to be huge.
And you need higher pressure.
And then you're cleaning this up with some CNC and key spots.
Yes.
The key thing I want to get across to you is that going from EVT with the CNC parts, sure, each unit is more expensive. Going from that to DVT, you're spending millions of dollars creating these molds, and now all of a sudden you have these molds that are quite hard to change. It's possible to change them. You can build them back up with welding, you can machine away a little bit, but you really only want to be making minor changes and hopefully no changes at all.
That's why we emphasize from day one, we do the thing in the right way for just once. One of the purpose of the EVT is that we want to expose the problems, issues, as much as possible.
It's important to explain what the difference is between the part cost. And I don't know if you know exactly for these parts, but certainly for the plastic, you said between $5,000 and $10,000 per CNC'd plastic parts. What will those cost once you injection molding them?
60 or 70 US dollars.
Oh, okay, that much.
Yes,
okay.
yes.
So 60 or 70 without the cost of the tooling. Yeah. What comes after DVT?
Then it's PVT. You basically solve the problems of the yield rate in the factory. In the production line, you have different stations, right? If for each station, the error rate 5%, then after one day, you accumulate hundreds of different defects components.
Sure.
Then that creates a lot of problems for the factories. So every mass production wants to increase the yield rate. It affects the efficiency of the production line.
At what stage are you figuring out what the assembly process is going to be, what each step is?
We are entering DVT right now. We're trying to have some trained workers to assemble the machine. You don't want to wait all the components from DVT to do the reliability test. That's why we kind of, even in the EVT phase, we try to do some reliability tests to verify whether the design is valid or not. So from day one, like when we first try to assemble our first EVT unit, we try to make our own SOP for that, and also the fixture for that.
Yeah. So the SOP would be the standard operating procedure.
So that along the way, we know where we need to improve for the next version. We want to minimize the human errors. So that actually sits inside the design of the flow of the manufacturing process.
And then what's the final stage?
Then it's mass production.
Mass production, MP.
Yes.
That's where you're just starting to ramp up your numbers. And
and then ship out
more and more
the
every
units.
day. And
Yes.
Awesome.
Yes.
So these are all the components for the print head.
Yes. So this is the UV light and then the heat sink for the UV light.
Yeah.
These two are the print heads actually.
Oh, this is the i3200 that
Yes.
you were talking about.
Yes.
So this has all those extra nozzles on it.
Yes, and these are some like slots going to this.
Yeah,
It
okay.
has 8 channels. We have a CMYK white plus vanish. It's 6 channels.
Yep.
So we have this interface, bridge this 6 channel to 8 channels.
Okay.
And then there are some PCB boards for the interface. We do have a camera at the bottom of the carriage. We can use that camera to tell which nozzles are blocked. We see this very small sensor. It's the spectrum photometer. And here's the lighting.
Okay.
And then this is the damper.
This is awesome. This is a super cool display. I think I'm going to head over and talk to Dr. Choi about what he's doing with calibration and the interface to the print head. I'm here with Dr. Choi. What is your role here at Morpho?
I'm mainly responsible for detecting the errors in the machine. Both the motion system and the print head, you have to make it work properly, but you cannot avoid any errors. So my role here is to detect the errors and try to compensate them during the printing.
What kinds of things introduce errors?
First, it is the motion system. Instead of extruding plastics, we actually fire ink drops, thousands of drops per nozzle per second. So if you move the print head very fast, you have to fire the drops really quick, up to, let's say, 20 to 40 kHz. We have 3,200 nozzles. You have to control them synchronously and to fire the drops on the right timing and at the right spot.
And you have to match that timing with the motion of the head, right? It's not just the right point in time, it's the right position of the head as it's flying across the machine.
Exactly. Single brain coordinating the whole motion of the system, the axis, and the print head. So this is a SoC system with FPGA capabilities that does the numerical heavy lifting, because you have to compute the nozzle commands. This type of print head, it is a piezoelectric type of head. So you drive the nozzles by controlling the waveforms, the voltage waveforms, in order to bend the piezoelectric materials. So it's like a pump. So you pull the liquid from the ink tank to the print head. Then you dwell a little bit, wait for the liquid to calm down, and then you just push it out. So basically the formation takes about tens of microseconds. And the flight of the drops is about 500 microseconds.
Wow, so you're just operating in tiny, tiny slices of time.
Yes, we have to calculate really fast. And the print head itself does not have any computation power. So all the numerical computations are completed by the FPGA on board.
So just for people who don't know, the SoC is like a CPU processor. So it's doing, your traditional instructions, kind of linear instructions, right? What you normally think of as a processor. But then the FPGA is something totally different, right? That's a field programmable gate array. Basically allows you to make custom logic that doesn't require instructions.
Like your graphic card, like GPUs. So this is basically the same thing as the heterogeneous computing.
Yes.
Like you do these days.
So the FPGA is the one actually generating the waveform of the voltages that get sent to the print head. Yeah, awesome. What is this?
This is a drop watcher. So before we see anything happening on the substrate, on the paper, we have to really detect how well the drops are forming. So the only way to do that is to really use a camera to look at the print head, which is this one. You can see these are actually dampers. On the screen, you can actually see what the camera captures. We have a strobe light here. So it flashes small amount of light every time. We fire a drop here on the print head, and then we do some kind of a delay, 20 microseconds. Then we flash the flashlight. Then we just open the shutter. So you can see here, actually it's not really very circular at the very beginning. You have a little tail called the ligaments. So basically there's some kind of fluid mechanics involved here. So the drops have to break away from the print head. What you have to do is to calculate the voltage, the waveform very carefully in order to pump out the exact amount of inks to form the drops. If you squeeze out the wrong amount, you will get smaller ones called satellites. They respond to airflows differently. So it becomes harder to land them on the right spot. So you will see a mess on the substrate.
You were mentioning that you're actually firing 2 little droplets out that join together.
They're actually all firing out by consecutive waveforms. So this is actually pre-calculated very precisely so that when they drop down, they will actually get put together into one big drops. Yeah.
Amazing. Is that an industry standard or is that something that Morpho is doing?
Yeah, this thing, actually, we built it ourselves. It's a custom one, cut down cost.
Is it industry standard to do the 2 droplets joining together? Is that normal for a piezoelectric head?
Actually, when I started out this business, I found some really great books that talks about the drops. There's one called The Science of the Drops. So basically, it talks about all kinds of fluid mechanics and waveform generation.
And so you talked about the waveforms. Are you doing different voltages at different times, or are they relatively digital on-off?
Actually, we have to do it at different levels. This thing actually is more like a resonator, like your average spring mass damper system.
Yeah.
So it's a second order system. All we do actually is to manage the vibrations. So when you start it, you have to pull in the liquid from the ink tank. You lower the voltage, so it starts to pull the liquid from the ink tank to the print head. Then you dwell a little bit because the fluids, they cannot move instantly. You have to give them a little bit of time to get calm. And then you push them out of the print head.
And so then you probably can actually mathematically model that spring.
Yes, we can do that. Instead of blindly doing DOEs, we actually have a model that guides us to tune the waveforms.
Interesting. And so then you were talking about the timing needs of the waveform for the print head needs to be matched up to the movement. How are you doing that?
That's actually very simple. So if you consider the movement speed of the print head, it's about 0.6 meter per second speed, and the acceleration is about 9 meters per second square. So it moves very fast. So you have to fire very quick in order to get a very small distance between the 2 drops. On average, if you want to, let's say, 17 micron distance, which is about the same as 1440 dpi, you have to time the firings like 20 kilohertz in order to match the speed.
But how do you know where the print head is at any given moment?
So we have different ways to do that. The very easy one is to look at the linear encoders. So when the print head moves, actually there's a reader gliding over a linear encoder.
Generally, they're like a clear tape with some black lines, and then you have the light going through it, and you get an on-off.
From 360 to 1440. It's quite complicated motion control. For the print head, we actually only control the speed. So we don't really worry about the position. So it's not set point control. We just move it as smooth as possible, and then we use a linear encoder to tell the print head when to fire. Exactly.
Oh, that's super smart. Then you can just literally use that as a timing signal to kick off your waveforms.
Exactly.
That's very cool. You had mentioned when we were talking earlier that you're doing some calibration and adjustments for imperfections in the rotation of the print head. So tell us about that.
So when you get a print head, there's certain manufacturing inaccuracies. Actually, it's very small. The error actually comes from the whole mechanism, the motion system. So there are imperfections in the timing bells, in the pulleys, and everything. So basically, we have a gantry system. We have the scan axis that's on top of the advance axis or the feed axis. So that's the y-axis, right? The 2 axes, it's really difficult to make them perfectly aligned. So there will always be some kind of misalignment. So it's not perfectly perpendicular, something like a 0.1 degree, but it's big enough to ruin the print. So we really have to detect the amount of errors inside the motion system and also how the print head is installed onto the rails. We detect it by looking at the substrates, the print. So we have to print some patterns specifically defined so that when we see the errors in the print pattern, we can actually calculate how the print head is misoriented.
How do you then look at that and figure out how the print head is oriented?
Yeah, there's some mathematics involved. Before I came here, I was working on robotics. In robotics field, this is actually very common. It's called kinematic calibration. So basically you have axis errors. All the axis, 6 axes of articulated robot will have errors. This is no different from that, only a little bit different mathematical model, but all the derivations of the errors is actually a standard inverse problem. So you look at the result and try to figure out what are the input errors.
What would have caused that error?
Just trying to solve a f equals fx equation. Given the y, you solve the x.
So you do some visual recognition of the way the pattern is misaligned, and you can build in some
it's kind of difficult to explain unless you look at the patterns.
This is super amazing work, and this is an amazing rig to be able to dial in all of those waveforms. It's super cool. You're doing amazing work. Thank you.
Thank you.
What are all the cloths for? Is this for secrecy?
to protect people from the UV lights.
Okay.
And also like if we want to take pictures using the zero vision camera system, we want to like make sure you have it enclosed.
Got it. But you don't have the enclosures for any of
To
these
save cost.
because it's so expensive to make the enclosure. So you're just using black cloths to
Yes.
cover them up. What's the story with replacement ink?
We have two types of ink cartridges. Despite of the standard one, we have another one that you can open it up and then refill. And we sell our own inks, like both in cartridges, but also in bottles, so that you can refill third-party ones.
And that's not the only way you're kind of opening the ecosystem, right?
Right.
Yeah. So tell us
So
about that.
if I remove this A4 tray,
Yeah.
you see there are like 4 months for you to install your own jigs. We will publish the dimension of those 4 months, including the electrical interfaces. We want people to design their own jigs because people, they have their own object to print on, right? And then we will publish an online tutorial to teach people how to take advantage of these 4 months and then including this electrical interface. We want to make sure that we give the power to customers.
Rather
so that
than
the people,
making it a closed ecosystem.
Yeah, we will also publish the SDK of the software so that their own jig can communicate through the electrical interface with the machine. And then we want the community to build up jigs on top of that.
Yeah. Awesome.
So that people can benefit from that and help each other.
So Brett, we've seen all of the guts of this and all of the fancy engineering and mathematics you're doing to make this work. We really haven't seen that many samples yet. Show me what this thing can do.
The board games.
Oh, this is super cool.
map
So
of the
you
board
have
games.
some up here,
Yes.
but this is like one of the tiles that you've made. So it's just on wood. This is gorgeous. How thick is this?
5 millimeters. We can go up to 2 centimeters.
Wow.
Yes.
This looks great. And you've got like shiny water, so you're controlling the varnish here.
Yes.
That's awesome.
And we have some digital swing.
Oh, like embroidery. This is it's so fine. It does really look like stitching. That's awesome.
Yes, we print this. We use Spanish to print these lines, and then we print 2 pictures.
So it's
on
like a
the different
lenticular.
Yes.
When you look at it one way, here, it's a pizza,
Yes,
and then you
then
tilt it.
Angle, it's a moon.
And then it's the moon. This is really clever. Are you going to have a wizard or something?
Yes, we have a
workflow to do
a
this?
special workflow for that.
Yeah, sweet. That's awesome. I really like this one. This looks like a very traditional Chinese engraving.
Painting, yes.
But the detail on this is magnificent. And with the patina on the metal, I wouldn't have guessed that this is UV printed. It looks hand painted or something, or hand engraved. This is an incredible machine. I can see how much thought and care and engineering work and hard mathematics you and your team have put into building a machine that's truly easy and a pleasure to use. If you would like to learn more and buy one of your own, click on the link down in the description. Brett, thank you so much for sponsoring this video and for teaching us so much about how you think about the process of making consumer products like this. I've learned a ton, so thank you so much.
Thank you. Thank you.
I'm looking forward to seeing this come out, and we'll see you again soon.